Good morning. Thanks for joining us today. We're obviously here from DMS Metering, and the CPD is going to cover heat metering technology. I'm going to do the first couple of slides, just give you a brief overview of DMS and where we sit within the market. I will then pass on to Chris, who's our technical director, and he will sort of run through the CPD. So DMS were established in 1999, and over the last 25 years, we've had massive growth. So we've been around for 25 years. We're actually the largest independent metering supplier here in the UK. We provide multi-utility metering, building services, FM, renewable. They're the sort of markets that we're in. Our whole scope is basically based on best in class for customer services, and that's what we pride ourselves on. We have exclusive UK supply agreements with world-leading manufacturers, and that's how we differentiate between other companies is we're actually a provider of the full service. So we're not just a box shifter. We don't just sell you a product, but we provide the full technical support behind every product that we sell. So some of the key features of our company: next day delivery, same day quotation, dedicated customer services, on-site support, commissioning, and we have a nationwide coverage. We're centrally based in Nottingham, so we're able to get to any part of the country within a few hours. Some of the key products and services, obviously, we're here to talk about heat meters today. So heat and energy meters is our primary focus. We do water, gas, electric, oil, and the others listed below. With regards to the solutions, we're involved in AMR, so billing, prepayments, and more recently, heat cost allocation, which is sort of started to become quite big for us. Some of the services that I've obviously already talked about: on-site support, commissioning, refurbishes, and site support. On the right-hand side here, we've got some of the key players that we actually interact with. So, for example, heat and energy, Suntex, we're the exclusive supplier of Suntex heat meters within the UK. Again, Apata, we're exclusive for their water meters in the UK. So every water meter that we would supply will come from them. And then Honeywell, quite important, Honeywell, we're actually the Northern European platinum channel partner for Honeywell. So all metering products, so gas meters, etc., will have to or all come from DMS metering. Even if you buy from another source, the main source in the UK is DMS metering. And then we look at some other suppliers like Siemens, for example. We do a lot of work with Siemens, and we supply a lot of their big mag meters. I'm going to pass over to Chris, and you can do the next part of it.
Thank you. Thank you, James. Yes, thanks for that, OS. So yeah, hello everyone on the call. I'm Chris, Technical Director at DMS. I've been a part of the company now for 20 years, so seen a lot of progression in the industry, a lot of change, legislation changes, meter changes, and everything else. So this more sort of slide is to cover the actual heat metering sort of profile of what's changed over the past 10, 20 years, in my experience. But what then is obviously going to be seen then moving forward. So today's slide is going to cover the heat meter size ranges, why we select certain meters for certain sort of reasons and certain applications. The UK regulations, which you've got sort of relevant regulations to abide by and stick to. Typical applications, so when you generally see heat metering and chilled metering as well, because that's becoming more of an entity in the UK as well. And then what sort of technology you've got. So mechanical, you've got ultrasonic technology and sort of superstatic technology. So what is different between the actual three measuring principles that is used alongside heat metering applications. Then we'll just discuss the sort of power options that you generally see in heat meters, the communication options, what actual heat meter looks like. Because I mean, some design engineers might see it on a drawing and never really know what they actually sort of experience sort of face to face. Technology selection, obviously what and why to select certain meters for certain applications. Heat meter installation, so installation parameters, a lot of you guys, and obviously on call as well, is where to install a heat meter. Very common question. It's getting it right first time for the application. And then obviously the temperature sensors as well, quite a key thing. You've got a term called MID, which is the Measurement Instrument Directive. And if you don't install temperature sensors correctly, yet again, it's obviously sort of an issue with regards to the application design. And then we've sort of generated, we've got a checklist that we actually still use in DMS to ask questions to customers. You can actually ask questions on your design. What is the checklist? What do you need to abide by? So heat ranges come in two sort of categories. Compact meters, which is generally for the sort of domestic applications, so domestic and small commercial. And then the commercial and the industrial meters are the larger sizes. So that's generally seen in sort of small commercial heat pumps now, LTXW systems, district heating systems, right up to the bigger sizes. So we differentiate between the two. Compact is small 15, 20 mil connections. That's something you'd see in your home or in a domestic apartment block, high-rise apartments. They're generally sort of supplied with a communication cable, which is very basic and simple, and that would lead you to a billing or a data collection platform. A lot of them now are either made in brass body, which is the standard default, or now a lot of manufacturers going on a composite route with regard to recycling meters in years to come. So a lot of manufacturers now are going down that of eco-friendly sort of design and recycling long term. Industrial commercial, yet again, you still cover the smaller sizes for certain reasons, because there might be certain data collection outputs that are seen on the sort of larger design models, but they go from 15 millimeter right up to DM500 and everything in between. So that generally covers anything district heating, anything sort of mediocre on small chilled or heating applications. Mains 24-volt batteries is sort of general sort of power supply for a lot of these meters that we'll sort of discuss today. And generally mounted on the actual body of the meter or the actual sort of wall of the actual plant room. And that's slightly different in relation to heating and cooling applications with regards to condensation or sort of atmospherics in the actual plant room itself. There's a reason why we push that on commercial industrial sort of design. They're mainly brass parts, but obviously you've now still got cast iron parts and obviously sort of stainless steel. So yet again, you've got three materials for that. You'll never see a composite meter on larger applications because the temperature might be too high. And it's not really designed for larger flows. It'll just sort of corrode over time and damage itself. And then obviously more application outputs with regards to larger models. We're talking BMS integration, wireless integration, everything else. So some UK regulations that sort of relate to a term called MID Class 2 or Class 3. So if we go back before 2014, before the sort of district heating and billing regulations that started off, there was acceptable use for either a Class 2 meter, which is more, obviously more quality or more accuracy compared to a Class 3. The difference between Class 2 and Class 3, Class 2 is no moving parts, highly sensitive, covers minimum flow rates, can be sort of repaired and obviously recalibrated long term. Class 3 meters generally were always mechanical. So it was always you moving parts. It was always reliant on the sort of the turbine, sort of spinning wheel, the pulsed output sort of design. That became a thing of the past. So really moving forward with regards to regulations, we still see Class 3 meters installed. They should not be installed no longer. They should not be specified on any application, should not be installed, should not be accepted, should not be purchased in the UK market. Like I say, some of your regulations that you'll cover and you've obviously looked into, no doubt, is the heat network regulation. So anything now that's either a domestic apartment that's got a central plant room that's more than 2 apartments or more is classed as a district heating network. Anything that's obviously city-based with regard to Sheffield, Newcastle, all the district heating networks that are actually happening around the UK, they have to have some form of metering either at building point or at entry level to the apartment, or a mix of everything. And that is a forced requirement now for anything that's new build. Anything that's retrofit old build, you have to do your sort of feasibility studies. Is it viable to change the actual sort of heating design? But a lot of people are being not forced down that route, but it's a better decision to do that, with regards to the benefit of, their money and their sort of eco-friendly energy sort of profile. Then you've got your Part L, which is the standard thing for building regulations around the UK. Cibse, And then heat meters used for non-domestic RHI, which I'll sort of step onto briefly. There was a government scheme, which was the Renewable Heat Incentive, which was to give people the incentive to purchase biomass boilers, install class 2 heat meters, and generate money back from the government to go renewable. Now that scheme's obviously now defunct, but it's a 20-year scheme, so it's still got another 10 years of life in relation to the applications that we see around the marketplace. We have a lot of contractors, a lot of installers that buy meters from us for their reapplication for the next 10 years of the RHI. So you might still see that in some commercial buildings that do have biomass boilers installed. You know, that is quite still a common thing. So just some example pictures. Where do you see heat meters or energy meters as well? More or less everywhere now. So low temperature systems. We're seeing a common term now called ambient loop. So that's like a combination of heating and cooling on the same network. Medium temperature hot water. So that's generally your bigger district heating systems that's getting the big temperature around the network into the actual building citywide. And then chilled water as well, individually sort of locations, but getting more common now with the UK climate and some sort of design factors that are happening in certain buildings. And then district heating and communal heating systems as well. You will generally see heat meters that are designed, specified, installed in those applications. Biomass, as I sort of stepped onto earlier on, the renewable heat incentive, that is a requirement to have heat meters installed. Like I say, scheme is defunct, but there's still demand for it moving forward for the next 10 years. And then HIU units or heat interface units, anything that's a domestic apartment now that's new build, would generally have a HIU unit designed inside, and that would generally have a heat meter installed for the billing, the prepayment, the sort of data collection methods. And a big thing now that is everywhere in the industry, ground source, air source, water source heat pumps. Yeah, on every design that we're seeing now, that you could kind of say is changing how HIUs are supplied in applications. It's becoming a heat pump. The main plant room application might not be a gas-fired boiler anymore because they don't want to do that, and that's quite a common thing now. But a heat pump would actually sort of solve that particular issue. So heat pumps now are being seen more as a design factor for the actual main plant room applications for certain buildings, and then the apartments would, you know, still have the heat sort of meters installed. So this steps on now the technologies. So we'll just go through the mechanical with regards how it operates, how or when not to use it. Anything that's mechanical, so this is a water meter, not a heat meter. It's got MID approval, but based on water volume, not heat volume. You know, there's still competition that we have out there that is selling these for a lower cost, viable option. But then when they're having to rip the meters out and start again, it doesn't become low cost, it just becomes a headache for everyone involved. So like I say, class 3 is based on the accuracy of a mechanical meter. As you can see with the image there, it's got a mechanical turbine. So it's reliant on the water going in and the water coming out and sending a pulse signal back to a display. That is then obviously sending that flow rate information to the display to calculate the actual heat energy. Yeah, it can't be used for domestic billing. It can't be used for the RHI, which is like I say, an old conversation. So the idea is to push the idea not to use it, not to design it. And this is reliant on the contractors that kind of sort of link to your specifications. If it's a price, it's sometimes what's cheaper. And this is what we're trying to educate on people. Not all about what's cheaper, it's what longevity, you know, 10, 15-year lifespan, something that's not changed every 2 to 3 years. And that's quite a common thing with a moving part, you know, wear and tear. If you're having to change, let's say 15 meters in 2 years, the price saving cover to start with was irrelevant to start with. So some positive, negative sort of comments about mechanical meters. So yes, they are easy to replace. It's basic conversation, basic sort of spares, basic parts, how they operate. All your European manufacturers stick to a standard. So if you take 1 meter out and replace it with another manufacturer, it generally goes in place, no problem. The positive is very basic to understand magnetic free pickup. So it's a 2-core cable that goes into a calculator. So a lot of electrical sort of contractors and even mechanical contractors understand the method. So to replace that, very simple. Dynamic range, because the mechanical meters have been around for so long, a lot of changes have happened with regards to the water industry to accept more flow rate going through the mechanical meters. But that's kind of irrelevant in relation to a heat profile. For a water profile, it's keep costs down because you can actually put more water for a smaller location. And all pipe size generally covered from the domestic size to the larger DM300s. Negatives is all down to water quality and how they need to be installed. So water quality is if you have a heating system that's not maintained over time, you get your crud inside, your inhibitor is low. Heating systems generally sort of eat themselves inside if they're not maintained correctly. Then what naturally is going to happen is they're going to eat the devices inside the heating system. So anything that's a moving part that's got bearings or anything like that will die and corrode over time. And that actually then causes inaccuracy readings. So the meter slows down, it sort of sticks, it stops. And that's where then the data is obviously lost as well. So with regard to large deposits in a system, large particles, because it's a moving part, you can get situations where that can damage the actual turbine inside. Smoothing paths, so that's in relation to your designs, is because you have to design them more straight up for pipe inside your systems. Instead of going for the 3 before, 3 after for the more sensitive meters, you have to go down the route of 10 diameters before and 10 diameters after. So you're installing more pipe work there at more cost, but no benefit at all because it's a mechanical meter that shouldn't really be installed in heating systems. So it's that sort of mentality to sort of think about as well with regards to design. Filters are recommended, and that's where, like I say, it's in relation to a water profile. So cold water filtration is important because it's RAS approval. Hot water is obviously sort of relevant for filters as well. It's more cost. You have to sort of do more design, more straight length of pipe. Plant rooms are getting a lot smaller nowadays, not bigger. So it's just that sort of challenge just to pass on to yourselves to basically get right. And then yet again, small particles can damage the actual meter, and that can cause obviously replacements to happen. And then with regards to the pulsed output integrator, if you have high voltage cable near a pulse, electromagnetic interference, you have something called sort of bounce back. So if that pulse doesn't get through to the actual display calculator, you can miss information as well. So it's just giving you some knowledge on what we see on a day-to-day basis and why we sometimes not argue over why that brand is different to that, but it's more or less it's the design, it's the approval that's quite important to us and really important to the client. Obviously, that's the whole point with what we're trying to sort of train people on. So the 2 other measuring principles would be, in this case, ultrasonic. So this is based on a tube. So it's a tube body. That is different than in different sizes, but the mentality is the same. Water passes through the tube. The tube has a circumference. It has something called a transit time signal. So what happens is it bounces a signal through transit time A, which is on the left-hand side there, and then bounces that signal in relation to the velocity of the water. The higher the velocity of the water, the higher the flow rate. So the meter would know then based on its circumference and its bounce or the speed, that is the actual velocity of that water at that time. If it's obviously a lot slower, yet again, the opposite happens. It's a slower flow rate, a slower bounce back, and that's the actual design. Ultrasonics can be used for class 2 billing by far. Anything HIU, anything RHI, anything that's heat pump related, anything that's got a billing request now, a district heating request, no problem at all. That is one option. Power supplies generally, battery mains. The pros and cons, same as the mechanical here, just as a comparison. I think by the end of today or tomorrow, you're going to get a copy of this slide, but I know you're recording it as well. So yet again, for reference for anyone, no problem at all. So ultrasonics have no moving parts. So that basically means they're long-term stable measurement. So generally, a lot of European manufacturers state at the moment, depending on country regulations and recalibration approvals that's currently happening in the UK, 10 to 15 years is about an average life cycle for a heat meter. So that would be an estimate based on how long a heat meter should be installed for. Still needs to be maintained on a yearly basis, or whatever the actual sort of building profile is, maybe 2 years maximum. But recalibration is a 10-year sort of cycle. So back to the smoothing paths, comparing to the mechanical, they're a lot less required. So I used to term it on 3 pipe diameters before and after. That is your absolute sort of minimum. So your design is a lot smaller. Yet again, saving some costs. The flow range covers 0.6 to 1,000 meters cubed, so they're quite sensitive to low flows on lower flow applications, and obviously big district heating systems, they're acceptable for high flows, and then more or less everything in between. So they're designed to measure the flow accurately, but we assist with why you select that meter for that certain branch, or why you can downsize a meter on a certain branch due to the flow rates to save some costs. So there's some further conversation to have on that. That's kind of involved in the checklist. They can be mounted horizontal, vertical, which is also why I sort of leave this to this point. The mechanical version can't be installed vertically. The mechanics don't allow it to happen. So also then you've got that mentality, if it's a mechanical meter installed in a HIU, where buildings generally are going up now, then you're installing that mechanical meter vertically, naturally, without even sort of recognizing it. So it's another thing, a design parameter to keep into the more expensive manufactured brands out there. The long term, the accuracy, the capture of data is where it's what it's all about. And then obviously wide communication options. All the high profile manufacturers now have a lot of unique data collection methods to get data. Sometimes now a mobile phone, a website portal, a cloud-based platform, billing invoices. You're not now limited now to actually how you get your data. Negatives, large pressure drop, depending on the application. So it's determined on how you size a meter up in relation to downsizing the profile. So the ultrasonic meter is based around having a smoothing path. It's based on having that water velocity going through it. If you downsize too much, naturally, you obviously get a large pressure drop through a meter. So it's balancing what's best for price, the application, and selecting the correct meter, which we're there on a day-to-day basis for that. Maintenance cost. So if, for example, you have a lot of installers, contractors that shorten cable, they cut cable because the display's up top and the meter's at the bottom, or vice versa, or there's too much cable coiled up and they just want to sort of hide it away. You must never cut any cable on any heat metering device, and really any metering device that's calibrated. All the cables are calibrated for a reason alongside the meter. So the disadvantage to ultrasonics is if you do cut cables, you generally have to replace either the temperature sensors, which is a low cost, but if you start cutting the actual signal cables between the display and the flow parts, you have to generally replace the whole meter. So, okay, a £200 device, fine, but something like a district heating plant that's £3-4 grand, yet again, it's slowing down. It's slowing the installers down to get it right. And if that can be put on your design as well, with regard, do not cut cables, do not do this, that would also assist then us with regards to the marketplace as well. Sensitive to particles and entrapped air. So, oxygen inside the system happens. You get trapped air in systems that aren't purged correctly, that aren't commissioned correctly, sometimes not commissioned at all. The meter knows this. If there's trapped air inside sort of dead legs or the meter chamber, or actually just flowing around the system naturally, the meter can sort of distort its flow rate over time, and that would also cause lower readings within the meter itself. So ultrasonics are more susceptible to air trapped. So it's just keeping that note just in case it's relevant for the application selection. Each measurement principle must be analysed individually. So the recalibration method, and this is where it's not fully accepted in the UK yet, but it's a conversation, is all meters would have to be taken out of the application and sent back to point of manufacture. But it can't be an on-site conversation at the moment. Quite costly. There's not legislation for that yet, but I think with how the district heating sort of regulations are going, there's going to have to be. So this is still a bit of a touchy ground moving forward. With ultrasonics at the moment, it's take out, send back to point of manufacture. It would work out cheaper just to replace the meter, strangely enough. Yeah. Measuring problems. So all meters have to have operating pressures. Ultrasonics do require 1.5 bar or more. If you have situations where you have a low pressure issue, end of line district heating system, a low pressure system as a whole, ultrasonic meters are not the meters to sort of use. You do have to have that operating pressure more than that. Yet again, something you probably wouldn't be aware of. Most systems are probably designed to 2 bar or more anyway, but we sort of put that in our sort of presentation because anything that was RHI biomass, generally 1 bar was the sort of default. And there's a lot of situations there where that meter was just not performing, not not causing the accuracy to happen on the system itself. And a big conversation in the industry now is glycol. So glycol now is becoming more relevant. Chilled applications are becoming more relevant. So actually glycol is being added into the system. You can buy glycol solutions now that have also inhibitor mixtures. So it protects the system as well as frost protection as well at the same time. Ultrasonics have started really recently to accept glycol programming, but you have to generally order it at point of manufacture. And if the percentage is wrong, then yet again, it's the conversation with the energy provider or the energy sort of consultant or you guys that actually that meter would have to be changed because the percentage is incorrect. So yet again, it's trying to save on cost. And then we move on to the superstatic or the static sort of measuring principle. So it's very similar to the ultrasonic. You know, there's an input and an output line of the actual body of the meter. You can see that just on the drawing there. It's obviously screwed connection, flange connections, just like everything else. They're all European standards, so class 2, as I've said, I'll keep banging on about that today. That is a standard sort of billing requirement for all our meters that we cover and have to cover in the UK. They are billing approved, they're RHI approved, and generally come with the power supply options that the system might need. How it operates is it's got a small venturi inside. So the flow passes through the actual chamber of the meter. It causes a slight back pressure. 10% flow goes into the actual the superstatic head, which you can kind of see on the sort of drawing there on the right hand side. And then it's 10% linear flow. So the actual pulse goes inside the head, which means 90% of the flow rate does not get seen by the transmitter itself. And it's directly proportionate to the flow that's actually being seen by the piezo electric sensor. So it's basically a vibration that's inside, very similar to the transit time. It's measuring the velocity or the speed of the actual pulse inside that then brings that flow rate data back to the actual main brains of the heat meter. Positive, negatives again. Let's go through some points. So static principle is based on no moving parts, long-term stable measurement, just like the ultrasonic. It's a static principle. It's a no moving part meter. It's class 2 approved. No effect from pressure impacts or particles within the flow. So kind of the comparison to the ultrasonic, if you have particles inside the system that can be bounced and seen on the actual transmitters, this is not being seen really by the actual the main measuring head, because 90% of the flow is actually not seen by the meter in question. It's just that ventura that's causing that that bypass pressure. Spare parts. So kind of the comparison that I said on the mechanical and the ultrasonics. If you was to, let's say, cut meters or damage cables on the static principle, the actual parts are available. So actually the cost conversation can be discussed. You can replace parts of that particular principle because it's not an ultrasonic design. It's a slightly different design that was weirdly enough designed by NASA back in the 60s, which is quite a common thing that I have to say during these CPDs, but they used it on the actual space shuttles for the liquid nitrogen system. So that's how unique the measuring principle goes back. And you could kind of say that measuring principle has been around for about sort of 50, 60 years. Yeah. So the point of that is obviously the independent measuring possible glycol is because it was used on really cold liquid nitrogen systems a long time ago, and it's been redesigned over many years. These meters are generally used now around European sort of continents involving cold climates. So Sweden, Finland, Norway, where heat pumps are very common out there. District heating is by far very common, but they generally have glycol in the system at large concentrations because of the actual outside temperatures that it gets down to during winter. So you can actually program that glycol on site. You can obviously order the meter based on a glycol sort of parameter. Yet again, that kind of gets to what I was saying about on-site support and programming and guiding people through it. The recalibration, as I said, not a legislation yet, but that particular measuring principle, the idea is to recalibrate the meter on site. So it's got a replacement part, which is the actual sense head that's on the body of the meter. So we're sort of set with that conversation if it was to happen with regards to that design, on-site support, on-site calibration. And again, early days at the moment, but it's an idea for, you know, contractors. And if we have to do that as a UK sort of country, then it's an idea for this early selection phase for the project, ready for what's going to happen in the 10 years of that that building itself. Complete flow range, very similar to the ultrasonic, obviously 1 to 1,500 meters cubed. So again, the actual accuracy of all the actual sort of meter sizes is within the 2% threshold. Negatives, limited flow options. So as a comparison to ultrasonics, you do have some sort of limitation on ultrasonic at a certain size has 2 or 3 flow options. The static option has 1 option per size. So that sometimes might incur the actual size is kept as it is, and we can't offer, let's say, a downsize option. But still, there's reasons why that is relevant for the design of the meter. 1 flow direction. So ultrasonics act in such a way, something called bidirectional flow, so kind of like backwards flow, bit of an alert, bit of an alarm. So it's very rare on heating systems, but that's sort of there for water systems where you have ultrasonic meters, obviously sort of with regards to water utilities that sometimes have back flushing and stuff like that, and they want to log what is relevant for the actual system itself. Because there's a bit more design into the body of the meter, there's obviously more weight involved. Really, 5–10% more weight is not a massive difference at all, but that's, like I say, that's in relation to the design of the manufacturers. Again, just to give you some visual on what a power supply looks like in a meter, if you're mechanically biased or electrically biased or a bit of both. Compacts, the standard that we see still quite a lot, which is quite surprising, but we try and guide people not to do it, is batteries. So batteries, fine, great. Cost saving to start with. You install a heat meter, you don't have to invest a few spur, an electrician, 3-core cable to actually get the power to that location. But the worst will happen because the battery at some point will die. And that is reliant on either the data collection output. Sometimes we see clients want it every 15 seconds. Bit silly, but it can happen. The standard default for district heating every half an hour. That's kind of like the London standard now. And some clients then go to 1 hour, 6 hours, 12 hours. It depends. As long as they've got a data capture for that day, they've got the difference between the day before to the following day. The more data you take back, the battery will last not a long time. Yet again, in our checklist, that's the sort of stuff we have to sort of enclose and ask. Generally, commercial, industrial, you have more options, way more options. Mains, 24-volt, switching power, AC, DC operation, that sort of stuff. That's more relevant for the commercial, industrial, and that's a standard because there's more data required for that because that's a profile, that's an energy profile, it's control, it's sort of asset management as well, it's alerts, alarms. You need data very quick. And like I say, mains power, you've constantly got that data, that power there to provide data every 15 seconds with no issue in the background at all. If you've never seen a calculator, a display, an integrator, people use different terms. What a display does, again, logs the data. It does all the calculations. It gives you all the output. All the electricians wire up to there. All of the mechanical mount the display onto a wall, depending on who gets the sort of job at the time. But generally, all our meters have a PT 100 or 500 temperature input, which is a part of the Class 2 requirement. Yet again, we design that with the meter, with the application. Very simple. All meters have something called an optical interface. So as I said earlier on, we offer product training. We kind of give people software, hardware to do the jobs themselves as well. So the application training we do, we like to do on site. So it might be a site visit cost. It might be a sort of demo day. If we can't do the actual job in hand at that time, we just pass on knowledge to a lot of the contractors to do it themselves. If they do it once, twice, 3 times, they kind of build a relationship with DMS and the products. Basically, it makes their lives a lot easier than actually just waiting for us to maybe come to site. Makes our sort of stress levels a lot lower as well, but it gives them more control over what they need to do day to day. And that could be a lot of sort of programming for the actual system. LCDs display, very basic. 2-button operation, very basic. The manufacturers keep it simple just to get raw data live or go into the historic data of its sort of internal storage. Basic part, front and base, it's just like a sort of separation part. You've got the base section that goes onto the wall, and the front section is the actual main brains. It just clips together. You can obviously seal them with regards to security methods, so no one can sort of tamper. very basic designs, but it's quite important to do nowadays for the energy sort of profile systems. And then some sort of outputs. Now, I won't go into this, sadly, quite a lot, but for the benefit of the recording as well, we have actually got another CPD that involves data collection methods, which I've discussed with the team before we sort of set this up. It could be an after conversation. It could be something where we maybe not come here and actually do a sort of team sort of call just to sort of cover that if that's of interest. But that covers more why to do data collection, what data collection methods they are. There's design drawing examples, might generate more conversation on some of the electrical side of yourselves. So it's something to sort of think about moving forward. But the main outputs that we always see in the marketplace is the optical readout. So that is a USB cable that goes into a laptop. The laptop has a piece of software that's relevant to the manufacturers. And then we give training for you guys or the contractors of the world to actually do the program themselves to set up the meter to the BMS. People love that. People want that. It makes their days a lot easier. And cost down as well. We have to charge for site visits. If someone can do it on site with our sort of telephone support or team support, it just works for a lot of people. MBus is the default for a lot of billing platforms. So that's just like a 2-core cable that is like a daisy chain, star topology, bus network. Analog outputs, now a lot of people are taking flow rate data from heat meters instead of actually adding another flow meter into the actual system itself. So it's using a heat meter to cover both aspects, both for heating and kind of control. Flow rate output 420 milliamp, 0 to 10 volts, kind of like inverter control. Modbus BACnet is still really the default because most data collection requirements go into a BMS. We all know why that happens. Yet again, there's extra cost to that, but it's a lot more faster data. So yet again, every system is different for certain data collection sort of requests. We have to facilitate everything. And then LoRaWAN networks, as it's called, is becoming more relevant in the UK. So this is wide area networks, wireless. So we're talking antennas in the centre of a city, picking up meters that are probably 2, 3, 4 kilometres down the road. That's where some of the some of our work and some of our infrastructure is going at the moment. So you're not having wires. So you're reducing the cost of labour to install wires on a network. You're just installing gateways and the meters that are not higher cost for the card, but it's an additional cost. But actually then the communication there, the labour cost of the wire is basically zero. So that could be a saving for a lot of our clients. And actually in the CPD, it does give you cost benefits of all the actual sort of data collection design methods. Wireless MBus, very similar to LoRa, just obviously a lot less distance. So they generally cover maybe half a kilometre range. So LoRa is basically the add-on to where wireless MBus has been for about 10 years. And then direct GSM, which not a lot of people do nowadays, but going back 5-10 years ago, it was still quite a common thing to do. They're still available in certain cases, but manufacturers now are just finding better ideas to kind of bulk, instead of one SIM card per device, is a network into one SIM card covering 150 meters. So, everyone's getting a lot more clever now to reduce costs. So why do we choose certain cases? So like I say, we've discussed mechanical, ultrasonic, superstatic, lower cost initially for the mechanicals, not suitable for any non-domestic RHI systems or any billing platform at all involving heat pumps as well. So really what we're trying to say now is that is now a thing of the past for heat systems. Don't use them, don't specify them, use the correct keywords for your applications. Ultrasonic, so long-term reliability within heating and cooling systems. So as I said to you, no moving parts, very sensitive to flows and everything else. So no problem at all. Different models required to cover heating and cooling combined systems. So ultrasonics do have a tendency where instead of having combined heating and cooling meters, when you purchase one or when you design one, you have to design it as a heat meter, as a cooling meter, or as both. We have a lot of clients that actually do get that wrong in relation to either asking that or some of our competition that actually gets that wrong in supplying that. Yeah. With regards to superstatics, long-term reliability within the heat and cooling systems. So yet again, just like the ultrasonic, no moving parts, debris in the system, no problem at all. Same model does cover heating, cooling, combined systems. So kind of what I said about the training and the setup and everything else. The static principle, because it's unique to ultrasonics, you can use it for both heating and cooling at a later date, or you can install it just on a heating system or a cooling system. It's actually got a bit of an AI in the background that knows the temperatures, and it knows how to switch itself in relation to what it's seeing at that time. That makes our lives a lot easier with regards to commissioning and actually supplying. And if there is any mistakes with the client where they've said that's the heating system, but actually it was a chilled, yet again, it learns based on the actual sort of difference of the temperatures involved. And glycol is obviously a sort of key point to that measuring principle as well. So typical heat meter installations. Yet again, visual on screen there, but I'll just go through the relevant points. So we always state and see and kind of push that the heat meters are installed on the return part of your system. Very important. Yeah. The purpose of that is return is the lower temperature. Yeah, there's generally less devices on the return. The pumps are generally designed on the flow. A lot of other devices are generally obviously supplied on the flow. So what you're doing is designing the meter naturally to be installed on the return to keep the heat meter body away from other devices. And that's generally the pumps. Yeah, pumps can affect accuracy of flow meters. Even flow meters next to pumps can affect the actual performance of a pump. So it's getting that balance right of what the pump installation parameters are compared to what the heat meter installation parameters are. Some get it right, some get it completely wrong. Very quick example, I had one last week where it was pump, it was a small straight off a pipe, and the meter was just next to that, and the flow was actually bouncing all over the place. And that's because the pump is designed to push water through a system, but in fact, oxygen, because you have the separation of water and air molecules that happen at the actual sort of pump cavitation phase, and that does affect the actual accuracy of the body. So we just state very basically, return, installation, unless otherwise stated. Yeah, because we can have that conversation where a meter is installed in the flow, might be completely away from the actual pump itself. But yet again, this installation parameters we have to know and actually have to program to the meter to say flow application. Yeah, that's the main thing to cover for installation. But like I say, recommended positions here. We have to think about high point, and the purpose of high point is air, oxygen finds its way at the highest point of the system. So that could be roof space, or within a plant room, it could double bend up and obviously go to the actual ceiling itself. If there's no air vents on that part of the section, yet again, it's going to find a particular chamber to sort of sit in. And that's generally going to be a heat meter body, a mechanical body, anything like that. So A, B, and D on that design drawing there is the standard way to install heat meters. Horizontal, no problem. Vertical flow up, vertical flow down. But try and avoid as much as possible on the C sort of location there. With regards to E, F, and G, as I said earlier on, you kind of base that on what happens on a flow side of the system itself. All of that is wrong. Close to a pump, close to valves, double bends. You've got to think about the water sort of physics point of view. You know, it has to be linear, and that's why you have straight over pipes in sort of design applications. Yeah. If you're close to a flow part of the system, there's always something that happens, and we have to justify why that happened, and obviously rectify as well, and obviously just to advise. And then temperature sensors, yet again, it's not difficult, but still there's some contractors that sort of cut corners. Temperature sensors that must be mounted inside either T-pieces, if we're talking about domestics. You buy T-piece valves that are kind of isolation T-piece valves that, you know, allow maintenance of the actual small domestic sensors themselves. Or then a lot of customers, anything 1 inch, maybe 40 millimeter above, they weld bushes into systems. Depending on the length of the bush determines on how the actual pocket sits inside. And yet again, just that example there, the pocket must be touching the flow of water to abide by MID. So it must be designed in a way that you're not designing a bush that's, let's say, 100 millimeters out of the pipework, and you've only got a 34 millimeter pocket that's going into a 100 millimeter bush. It's not touching the flow of water. It will still calculate energy, but it will not capture the true energy of the water. You could kind of say there's a small air pocket inside. And we've done some trials tests over many years, and even out by about 1-2 degree can happen on that. 1-2 degree over a 24-hour period, probably not considered a lot, but over a year, over 10 years, you're not capturing that energy correctly. So it's very important to install a pocket on the MID design. And then, yeah, just our basic checklist. But heat meter, what do we select? Static, you might have glycol in the system. Client might have a large heat pump network. Yeah, we would select that. Ultrasonics might be heating and cooling. No glycol involved. Want something quick off the shelf, anything like that, ultrasonics would be an option. Mechanical, yet again, we do supply mechanical heat meters, but we do build up the brick walls with regards, you need to be told like this, and you need to obviously accept that it might not last 2, 3, 4 years. People still want to just do basic heat meter monitoring for mechanical for their own internal benefits, not for billing, just for a reference point. That's still fine if you're not drawn by government legislation, because sometimes government legislation is to a boundary, and anything after that, sometimes a university campus, maybe something like that, it's their own property. They're just allocating heat. They're not really billing for it, yeah? So there is a crossover as well. Yet again, chilled, LTXW, medium temperature hot water. We need to know what we're dealing with regards to that network, what temperatures, what best to then select in relation to the static, ultrasonic or mechanical. Approval requirements, class 2 or 3. Yes, we'll still have that question. People still are aware of the class 3. Some people still don't know about the sort of difference between 2 and 3. That's all linked to the actual point 1 and 2. Is glycol present? Obviously the brand. So we deal with direct manufacturers of glycol. So, I mean, I won't bang out names, but there's a lot out there. We've got the fingerprint of their glycol solution that is actually implemented into the manufacturer's software, because glycol does change density and specific heat of the liquid. Some people just think glycol is glycol. It's not. There's about 120 solutions now that are in the UK market. They all act in different ways, yeah? But we have to ask that question for a reason. And then we're going to residential, industrial, commercial. What's the application you've got? Pipe size, flow rates. So, I mean, a lot of your stuff is going to be early design drawings, maybe stage 2, 3, 4 at some point. Yeah, if we're doing estimates, fine, a pipe size is okay for now, as long as we get some of the actual basics there just to generate a price. And then from there, it gets obviously more nitty gritty. Stage 3, stage 4, what you take away from the actual drawing, how can we help with sort of cost reduction for the actual sort of construction company and the actual sort of contractors. Yet again, all this is linked to sort of save some cost long term. Flow and return, as I said earlier on, quite key. We ask that's probably our most common question at the moment, because a lot of people now are all looking at the correct programming of meters, and it does make a difference. And then power, what you need. Communication, what is the data collection sort of method? What is the actual sort of BMS company looking for? And then the temperature sensors. Dry type is the actual pockets that go into the T-piece, as I explained earlier on. And the wet type sensors or direct sensors are basically direct contact with the flow of water, generally seen in domestics. But if you actually pull those sensors out, it generates a leak. So that's kind of a security mechanism for anything that's domestic. You get a lot of obviously sort of tamper situations for, communal heating systems, tenanted apartments. It's more of a security measure that if someone takes out the sensor, yes, you can be fraudulent with heat meters, but they'll have a nice puddle on the floor at some point. And that's sort of the end of the CPD. I mean, any questions, anything like that, or even if there's questions after today, you know where the contact is, and we can go from there.